In July 1969, as the Apollo mission was approaching the moon, it had to momentarily turn its boosters on again. And this was done to slow the spacecraft down so that it could enter into an orbit around the moon. Now, these landing procedures are pretty common in space exploration, and they're a problem faced by every probe, spacecraft, and instrument that's sent out to space. And it's a problem because this means the spacecraft has to carry extra fuel on board just to be able to pull off these rocket burns. But why is that? Why can't a spacecraft just slow down on its own, the way cars do as they're coasting along? After all, if we turn off their engines and let them coast along, cars will also slow down and then eventually stop, right? We're going to try to explain this using Newton's first law of motion, which states that in the absence of a net force, an object at rest will remain at rest, and an object in motion will continue its constant motion. And this is also called the law of inertia. Let's translate this. Well, this means that unless there is a force acting on an object, it will just continue to do what it was already doing. In other words, without force, the object will not experience an acceleration or a deceleration of any form. And that's exactly what's happening with the spacecraft. In space, there is usually no net force acting on a spacecraft, which is why, unless they use their boosters to slow down, they will continue to move in a straight line with the same velocity and end up missing their target. But this is not true for cars. Cars experience resistance forces due to friction, and this is because of friction with the roads and the air. Which means cars need the engine running to balance out these resistance forces by applying a forward thrust, and that's how they move forward at a constant velocity. But in the absence of this thrust provided by the engine, the car will experience a net resistance force which should slow it down with time. And we can actually observe this phenomena ourselves too. Let's look at one such example, where we'll be balancing out forces acting on a moving object to produce a net force of 0. Now the setup for this experiment is really simple. We have a trolley that will be rolled down an inclined plane. The inclined plane itself is at an angle so that the force of friction acting on the trolley is equal to the force of gravity pushing the trolley forward. And this is called a friction compensated plane. Now we're also going to attach a speed measurement device to the trolley so that it records the trolley's speed as it rolls down the inclined plane. Now since the force of friction is balanced out by the force of gravity on the incline, when you push the trolley, it'll slide down at a constant speed. And that's something the measurement device will actually show you in numbers. Since there's no net force acting on the trolley, the initial speed it gets when it's pushed is the speed that it will maintain throughout. And we can also observe resistance to motion for a stationary object that isn't experiencing a net force. Now, if you've ever seen those movies where the movie star will pull the cloth from underneath the table while it has all the cutlery and everything on it, you'll know exactly what I mean. As they pull the cloth, it experiences a really strong force and thus accelerates really fast. Now, objects like plates and cutlery that are lying on top of the table, they don't feel that force, and that's why they remain stationary and the cloth comes out clean from underneath. Just as Newton's first law of motion dictates, any object at rest will remain at rest unless acted upon by a net force. And you can actually replicate this at home too, not the tablecloth. Don't wreak havoc on your house like that. Just put a coin on a smooth piece of paper and then very quickly pull the paper out from underneath the coin. You'll notice how the paper slips right out, but the coin stays in its place. And that's the reason why spacecrafts and even large ships on the ocean have to actively use energy and power their engines to slow down. Otherwise, as Newton's first law of motion states, they'll continue to move in the same direction.